Alright, silly people, here's the situation. We're going to be plotting the period of enharmonic oscillators given a amplitude for an enharmonic oscillator. But first, we have to do a proof, and it's going to start with this equation for energy, which is just sort of the standard equation for energy. It's kinetic plus potential, right? You have to solve it for dx dt and then integrate it to get this equation here. So for this, I'm just going to show you what I did in LaTeX. And so, yikes, that's a spoiler. So you start with the equation, yeah. You sub E for V of A because conservation of energy says that the energy is going to be the same as the potential at the amplitude. So you do that, and then you rearrange stuff and take a square root on both sides to get this expression for dx dt. Then you solve it again. You put the dx on the right-hand side over the radical of VA minus Vx. And on the left-hand side, you keep the root 2 over m, and then move the dt to the left-hand side. So at that point, you can integrate both sides. You can see the integration is from 0 to t over 4 on the left-hand side, and the amplitude, which corresponds to t over 4, is literally just the amplitude of the enharmonic oscillator. So you put the amplitude on that side, and then you do the integral on the left-hand side, just is going to give you t over 4, and then you simplify a bit to solve for t. You get root 8m, integral from 0 to a, of dx over the square root, yeah. So, and then the rest of this problem is to do that integral via Gaussian quadrature and plot on a range of periods 0 to, or on a range of amplitudes 0 to a, the result of t. So, I mean, this is going to be actually very similar to the last problem. Of course, we're going to start with defining the integrand. So the integrand is going to be def f of x. It just looks like 1 over the square root of v of a minus v of x. Now, v of x is x to the 4, and just realized I should put the amplitude as an argument into the function. So if v of x is x over 4, then v of a is just a amp to the 4th, and then you do minus x to the 4th, right? Nice and simple. And then we're going to define the function to do the integral t of amp, and then yeah, it should just be t of amp. It's the only argument we're going to put in. With n equals 20 slices, the starting point for the integral is always 0. The end point for the integral is the amplitude, and then at this point, it's just the Gaussian quadrature sort of example code again, which I did do up here in the last problem, so I'm just going to grab that. Stick it down here in the function. And then whenever we have the integral done, we just multiply the integral by, you return s times the square root of 8 times m. Lovely that. Then you plot it. We'll just go ahead and import matplotlib.pyplot sblt, and then again, this sort of infrastructure for the integral is not array safe, so we're going to have to create an array of amplitudes for the thing to run over, which is going to be the lens space, and it's going to run from 0 to, actually let's not have it run from 0, let's have it run from 0.001, and I'll explain in a minute why. But then go to 2 in 1,000 steps, and then just do 4 amp in amples t, and then I should create an output list for the periods. So it's just going to be TLS empty list TLS dot append TLS, not TLS, T of amp, of course. After that, you actually plot amples versus teals. And then in the function call in the Gaussian quadrature bit, you actually do want to include your amplitude in the function call. Then it should be good. Right? Oh, m is not defined. I guess I should, yeah, m is going to be 1 according to the problem statement. And then you get something that is crazy like this. So turns out with amplitudes that are close to 0, this radical that is on the bottom of the integral becomes really, really small because you have v of a minus what is essentially v of a. So not great, and it kind of shows and it becomes really large. But then the values after that kind of make a little bit more sense. So I wonder what will happen if I jump this forward to 0.25 instead of 0 and see the sort of behavior I see then. Okay, yeah, that's a lot clearer. The amplitude tends to get smaller, or yeah, the period tends to get smaller as you increase the amplitude. But then if you decrease the amplitude, it gets quite a bit larger, which is funny. All right.